Welcome to this course. You must have already heard the 2-minute video in which I spoke about the importance of calculus, but the fundamental to every mathematics is numbers. Without numbers, there is no mathematics. So ultimately, mathematics has to speak about numbers. So today we will start by talking about numbers and trying to understand some of their important properties. First and foremost, we speak about natural numbers. Natural numbers are essentially natural. 1, 2, 3, 4, 5, 6, 7, 8, 9. I really don't have to make an explanation to you about these things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever as it goes on is the numbers we use to count. We use them for counting everyday objects. We use them for counting money. We use them for keeping dates. So these numbers are absolutely natural, and remember, this number starts with 1, and with 1 you keep on adding 1, and then go on, it just goes on and doesn't end at all. This moving on without stopping is what we say moving towards infinity. Now some mathematicians would like to add 0 to this subset of numbers, where 0 is a number which signifies that there is nothing. Then came negative numbers, which you are aware of, and the collection of negative numbers, the natural numbers and 0 gives us the set of integers. Now what is a negative number? The question would be very natural, because Blaise Pascal, a very famous mathematician about whom which you have possibly heard about in high school when you study binomial expansion of two numbers. So you must have heard about Pascal's triangle, which gives you the coefficients that comes in by different binomial expansions. So Pascal once made a comment that for him it is difficult to imagine how can you take away something from nothing. So the issue of negative numbers became very big, rather a philosophical issue, but to understand negative numbers, just you can look into the idea of a credit card. So if you have a credit card, you go, when you get a credit card, you get it for free. So there is no account, you have an account, but you have no money there. So when you go and swipe a credit card, you essentially are borrowing money from someone else, borrowing money from the bank whose credit card you hold. So this process of borrowing means that you owe someone some money. So at this moment, that money is really not your money. To signify that fact that you have borrowed that money, a dash sign is put in before that, and that introduces what is called a negative number. We say that you have a negative balance on your account. So it's a very good way of showing what we are short of. So negative numbers thus is a very natural extension of our basic working in daily life. Along with the negative numbers, positive numbers and 0, the natural numbers, negative numbers, -1, -2, dot dot and 0, we form what is called the integers. After that, the most important number possibly is a fraction, and we know everything about a fraction. We were taught in school that you have 5 pieces of cake and there are 6 people standing. How will you equally divide the cake among all the 6 people? So that these sort of small questions are actually teaching you about fractions. So fractions or rational numbers are essentially numbers which can be expressed in the form p by q, where p is an integer and q is an integer. Rational numbers, of course, has both negative rational numbers and positive rational numbers. So long back in antiquity, during the time of the famous mathematician Pythagoras in Greece, there was this concept that in this world we just have the whole numbers and the fractions. There was nothing else, and everything has to do with numbers. That was Pythagoras' dictum. But these are the only things that we have. Then one of his disciples used his famous Pythagoras theorem in geometry to show that there are some numbers which are beyond the standard fractions and whole numbers that we know. So, consider a right angle triangle whose both the perpendicular and the base are of 1 centimeter each. Then you come to a number called root over 2 as the length of the hypotenuse, because if this is as Pythagoras theorem says, so this square of this side plus square of the base plus square of the altitude gives you the square of the hypotenuse. So, this side I call A and this side I say B and this side is C, and C square is equal to A square plus B square. And if A is 1 centimeter, B is 1 centimeter, then C square is 2 centimeter. So, C, because it is the length, we cannot take the negative root. So, it is root over 2 centimeters. So, it is one of the most important things to know that root over 2 cannot be expressed as a fraction. And I will leave you to do the proof in the exercises. So, if you root over 2, you cannot write it in the form P by Q. Of course, there are many other numbers which are not of the form P by Q, where P and Q are integers and Q is not equal to 0. Of course, you can ask me this, that what would happen if Q is equal to 0. So, such a thing is not defined, so we can just improve our writing a bit here. So, now these numbers which cannot be expressed in the form P by Q are called irrational numbers. So, root 2 is an irrational number. Similarly, root 3 is an irrational number, and so is root 5. So, these are some very basic facts about numbers, and now we are going to talk about the fact that the given fraction can be expressed in many different ways. For example, if I take half, I can multiply both sides on top and the bottom by 2 and I can get 2 by 4, or I can multiply by 3 and I can get 3 by 6. So, all of these are equal to half. So, basically give me a fraction P by Q, and if I have a number K and if I multiply both up and down by K, then K P by K Q is always P by Q. So, given a fraction, there are many other fractions which are actually equal to this. This is essentially the notion of an equivalence class, about which we are not going to speak in detail. So, now what is the main use of natural numbers? Its main use is counting, and you know that we use 1, 2, 3, 4, 5, 6, 7, 8, we count everyday objects. Now, how do we actually count? If I have a say few cups, say I have a bag which has 5 cups, teacups, and then there is a bag which has saucers, means plates. Which things I have more, cups or saucers? That how do I decide, even if I do not know to count? How would I do if I do not know about numbers 1, 2, 3, 4, 5, 6, 7, 8, 9? The best way to do is to put a cup on a saucer. So, I put this one on this, the third cup on this, the fourth cup on this, and the fifth cup on this, and I then see the one saucer is left out, which means that the number of saucers or plates is strictly bigger than the number of cups. So, what you are essentially doing this can be marked as 1, this can be marked as 2, this can be marked as 3, this can be the first, second, this one marked as 4 and this one marked as 5. So, I can mark this cup as 1, this cup as 2, this cup as 3, this cup as 4 and this cup as 5. So, I am using an abstract numeral to signify a cup. So, the same number 1 is signifying a cup, it is also signifying a plate. So, 2 is the second cup is also signifying this cup as well as signifying this plate. So, essentially counting means putting a set of objects in one-to-one correspondence with the set of natural numbers. For example, if you have say 5 objects, say A, B, C, D, E, then how do you count it? So, you say okay, A is the first object, B is the second object, C is the third object, D is the fourth object, E is the fifth object. So, there are 5 objects. This is, of course, you can count, this is a finite set. In the same way, if I have say an set containing F, G and H, so this is the first object, that is you are relating A with F, this is the second object, this is the third object. So, you are essentially relating H with C, B with G, but there are 2 objects more in the sets which I can mark here as A and which I can mark here as B. So, the cardinality, the amount of elements in a set is called the cardinality of the set. So, the cardinality of this set A here is 5, that is the cardinality of A, and this set the cardinality of B is 3. So, cardinality of A is more than cardinality of B, so B has more elements. What is more fundamental is what happens if my set is infinite. It has elements, the number of elements do not end. For example, the set of even integers, and this was first observed by Galileo. So, even natural numbers. So, what you do with even natural numbers? With even natural numbers, that is, this is a set consisting of the numbers 2, 4, 6, 8, 10 and so forth, it does not end. How many objects are there? And then also take the set of odd numbers. That is 1, 3, 5, 7, 9 and so forth. Now, are these 2 sets countable? Yes. The sets are countable in the sense because 2 is related to 1, 4 is corresponding to 2, 6 is corresponding to 3, 8 is corresponding to 4, 10 is corresponding to 5 and so on. And similarly, for the odd numbers, 1 is corresponding to 1, 2 is corresponding to 3, 3 is corresponding to 5, 4 is corresponding to 7, 5 is corresponding to 9 and so on. So, both these sets, even numbers, set of even natural numbers and odd natural numbers are countable. But the remarkable feature, though these 2 sets are subsets of the set of natural numbers, the elements of these 2 sets, the cardinality or the cardinality of this infinite set, if that has any meaning, that cardinality is same as the cardinality of natural numbers. The infinite number of elements that these 2 sets has is same as the infinite number of elements the set of natural numbers have. This is very counterintuitive, but this is what was shown first observed by Galileo and later taken as that very definition of counting and a very basic idea of what infinity is. If I want to talk about infinity as a number, it was first studied by George Cantor. So, essentially what we have done, that when we are talking about counting, we are essentially putting a set in one-to-one correspondence with the set of natural numbers. That is, there is a bijective mapping. Okay, I have not spoken about bijective mapping, but you can understand this very basic correspondence. This is like a child's play. The interesting feature is that not only this set is countable, but the set Z, the set of integers, this is countable. So, essentially you have to find a function to show that if Z is countable, the job is to find f. So, here I said that a set A is countable if I can set up this bijective map. Similarly, if Z is countable, I have to find a map, a bijective map from N to Z. So, in your homework you will check out how do you set up that bijective map. Bijective map or one-to-one correspondence, and most people would know about bijective maps etc. they are taught in high school, but we will talk about them in our next lecture. How do we show that Z is countable? The interesting feature of showing Z is countable is done in the following way. So, first take 1, write down the numbers in this way, put 1 in the denominator and then just write all the natural numbers in the 1 in the numerator and all the natural numbers in the denominator. So, 1 by 2, 1 by 3, 1 by 4, 1 by 5th. So, then you start with 2 in the numerator and all the remaining numbers are put in the denominator, 2 by 2, 2 by 3, 2 by 4, 2 by 5 and so on. Similarly, for now you take 3 in the numerator and rest in the denominator. Of course, there is repetition, 1 by 1 is same as 2 by 2 is same as 3 by 3. The way Cantor taught us to count, I will just write the name, it is very important to know the name of this famous mathematician who spent the last part of his life in an lunatic asylum, because people thought he was mad because he was talking about actually handling infinity like a number and not just philosophizing about it or just telling that it means that you can just grow without bound. So, here the step is the following: you start with this one and go to the right, then come down to the left, go down and go up again and then go here again, and again do the same thing, go to the right, come down to the left and so forth. So, you have to come down absolutely to the left like this. So, and just go on. So, this from here again go to the, from here you go back again. So, here from whatever is the number you go back here and here and here like this. So, this procedure that we have just shown, it can be used to show that this is countable. So, you are now counting 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. So, basically we have been able to set up this map. So, what we have now shown that the set of rational numbers Q, we have done it for the positive part. So, you same for the negative part. So, set of rational, or you can put plus minus does not matter. So, you can put 1, 2, 3, 4 like this. So, Q or set of rational numbers is a countable set. The set of rational numbers along with the set of irrational numbers forms what is called the set of real numbers, and we are supposed to study about real numbers, because calculus essentially handles real numbers and functions defined over real numbers. Now, I just would like to stop here by making this famous result known to you, that the set R is not countable, that you cannot set the set R in one-to-one correspondence with the set of natural numbers. So, the set R is not countable. This was also first shown in 1874 by by Cantor. So, with this I end the talk here, which gives you a very brief idea about what numbers are, and in the next talk we are going to talk about functions. So, to give you what are the very basic properties of functions. So, thank you very much for your attention.